On Rapa Nui, the first clue is not a statue, it is a patch of ground. For years, ancient rock gardens helped support a familiar story. A large population grew beyond the island's limits, exhausted its resources, and collapsed before Europeans arrived. Then research mapped those fields again. The agricultural footprint was far smaller than expected. So if the famous collapse really happened, where is its archaeological signature? Rapa Nui lies roughly 3,700 kilometers west of South America, near the eastern edge of Polynesia. Polynesian settlers reached it around the 13th century. Over the next several centuries, their descendants created one of the most recognizable monumental landscapes on Earth, hundreds of stone platforms, or ahu, and the enormous human figures known as Moai. When Europeans first reached the island in 1722, they found something that seemed difficult to reconcile with those monuments. The island was largely treeless. Its population appeared modest. The Moai implied immense labor, yet the landscape looked stripped and exposed. That contrast became the foundation of one of archaeology's most famous cautionary tales. In the strongest version of the story, Rapa Nui once supported a population far larger than the one Europeans encountered. Forests were cleared as people expanded agriculture and built monuments. Timber was consumed for fuel, construction, canoes, and perhaps for moving statues. As resources disappeared, food production failed. Competition intensified, society fractured. By the time outsiders arrived, they were supposedly looking at the remains of a civilization that had already destroyed the ecological system supporting it. The idea was powerful because it seemed to connect everything. No large trees, giant monuments, a small island, and a small contact-era population. And there was no question that major ecological change had taken place. Rapa Nui had once supported a palm-dominated forest. By the time Europeans described the island, that forest was gone. The disagreement is not over whether the environment changed. It is over what happened to the people while it changed. A society can alter an ecosystem without undergoing a catastrophic population collapse. Environmental stress can produce adaptation instead of immediate failure. And if Rapa Nui really experienced the kind of demographic boom and crash often described in popular accounts, that event should have left evidence that can be tested. One of the first places to look is food. Rapa Nui is not an easy place to farm. Its soils developed on volcanic rock, but age, rain, wind, and nutrient loss created serious agricultural constraints. The people who lived there responded with techniques adapted to those conditions. One of them was rock gardening. Farmers spread or concentrated stones across cultivated ground. This was not decorative. The stones could reduce evaporation, influence temperature, retain moisture, and alter nutrient conditions around crops. Sweet potato was especially important, alongside other terrestrial foods and marine resources. To an archaeologist trying to estimate ancient population, these gardens are more than traces of farming. They are a rough measure of productive infrastructure. More intensive cultivated land can potentially support more people. So the area covered by rock gardens became important to population models. Earlier remote sensing work suggested that these modified fields might cover anywhere from about 4.3 to 21.1 square kilometers of Rapa Nui. Those estimates carried substantial uncertainty, but they became inputs for models that allowed much larger pre-contact populations. Under some assumptions, estimates climbed above 15,000 people. That created a clean demographic arc. A large population rises, agricultural pressure increases, ecological limits are crossed, and then the population falls. The entire argument depends in part on getting the agricultural footprint right. In 2024, a team led by archaeologist Dylan Davis revisited that footprint using higher resolution Worldview 3 satellite data, archaeological observations collected on the ground, and machine learning classifiers. The important part was not that a computer looked at the island. It was what kind of information the satellite could see. The researchers used shortwave infrared imagery. Different soils, rocks, vegetation, and moisture conditions reflect and absorb wavelengths of light differently. Those differences can make features visible in data, even when they are difficult to distinguish in an ordinary photograph. The team trained its models using rock gardens already identified through fieldwork, then applied the classification across the island. They also manually checked the output and removed obvious errors. The result was dramatically smaller than the older estimates. The surviving rock garden area identified by the study totaled about 0.76 square kilometers. The researchers found that some areas previously classified as ancient cultivation included natural lava flows, colluvial deposits, vegetation, and even modern roads. Their estimate was roughly 1/5 of the most conservative earlier island-wide estimate. That does not give us an exact census of ancient Rapa Nui. Some gardens may have been destroyed by later development. Small cultivated areas can fall below the resolution of satellite imagery. Not every calorie came from rock gardens. People also used other soils, grew other crops, and exploited marine foods. Agricultural productivity changes from year to year, and the amount of land under cultivation could change over centuries. The authors were explicit about those limitations. Still, when they recalculated how many people the mapped rock gardens could support, the implications were difficult to ignore. Across their modeled scenarios, the average carrying capacity from rock gardening alone was around 2,000 people. When the researchers added a rough allowance for marine foods and other terrestrial production, they arrived at an estimate around 3,000. Under the most optimistic rock garden productivity scenario in their table, the figure reached 3,901. That number is often misunderstood. It is not proof that exactly 3,901 people lived on Rapa Nui. It is not a hard ceiling for the entire island under every possible diet or farming strategy. The study itself says that a comprehensive reconstruction of prehistoric population size requires more work. What it does show is that one of the key pieces used to support very large population estimates appears to have been substantially overestimated. And that creates a problem for the classic collapse story. If Rapa Nui once held 15,000 or 17,000 people, where is the agricultural system that sustained them? Maybe parts of it are still missing. Maybe some forms of cultivation leave weaker traces. Archaeology rarely gives us the luxury of complete records. A collapse hypothesis makes predictions. A huge population should leave more than a compelling story. It should leave signatures in the land, in settlement patterns, and eventually in the people themselves. The fields were the first test. They did not produce the answer many people expected. The next test would come from something harder to erase than a garden: DNA. Unlike a field, a genome cannot tell us exactly how many people were standing on an island in a particular year. What it can preserve is something different: the history of how populations changed over generations. When populations shrink dramatically, genetic diversity is lost. A severe crash can leave a bottleneck, a detectable narrowing in the ancestry of the people who survive. That makes genetics an unusually useful test for the Rapa Nui collapse hypothesis. If a large population had fallen catastrophically before European arrival, especially within only a few generations, researchers should at least expect to find some demographic signal consistent with that decline. In 2024, an international team published whole genome data from 15 ancient Rapa Nui individuals. The remains had been taken from the island during the 19th and early 20th centuries and were held at the Musée de l'Homme in Paris. 11 were directly radiocarbon dated. After corrections for the marine foods in their diets, the individuals broadly fell between 1670 and 1950. That range requires care. Most of these people lived near or after first European contact in 1722, and genetic models do not reconstruct history with the precision of a written census. But the researchers could still ask a critical question. Was there evidence that the Rapa Nui population had undergone a severe collapse in the 17th century before sustained European intervention? Their answer was no. The demographic models were not consistent with the enormous pre-contact population followed by the sudden crash required by the strongest versions of the ecocide narrative. Instead, the researchers reconstructed a relatively small population that expanded after settlement and remained resilient through the centuries before European contact. This does not prove that nobody died during drought, conflict, crop failure, or any other period of hardship. Effective population size, the quantity geneticists reconstruct, is not identical to the number of living people at any single moment. The result is important for another reason. It agrees with the agricultural evidence. Two methods measuring completely different things had now run into the same problem with the classic story. Satellite mapping found less intensive farmland than expected for an enormous population. Ancient genomes failed to reveal the severe pre-contact bottleneck that an enormous collapse should have produced. Neither finding alone closes the case. Together, they make the old demographic curve much harder to maintain. Then the genomes revealed something the collapse debate had not been designed to answer at all. Every one of the 15 ancient Rapa Nui individuals carried a component of Native American ancestry. On average, it represented roughly 10% of their genomes. There was essentially no European ancestry in those same individuals. Using the size and distribution of Native American ancestry segments combined with radiocarbon information, the researchers estimated that the admixture event occurred approximately between 1250 and 1430. That is centuries before Europeans reached Rapa Nui. The genetic evidence therefore supports pre-European contact between Polynesian ancestors of the Rapa Nui and people from the Americas. What it does not tell us is exactly how that meeting happened. The DNA cannot identify which shore the encounter took place on. It does not prove that a Rapa Nui canoe landed on the South American coast, nor does it prove that Native Americans reached Rapa Nui independently. Genetics can reveal that populations met. Reconstructing the voyage itself requires other evidence. Even with that limitation, the finding changes the scale of the society we are looking at. Rapa Nui was isolated geographically. Its inhabitants were not necessarily isolated navigationally. Their ancestors were part of the extraordinary Polynesian expansion across the Pacific, a movement that populated islands separated by distances that still look immense on a modern map. Pre-European American ancestry on Rapa Nui adds another piece to the evidence that Pacific voyaging networks were capable of connections once treated as improbable, and that matters when we turn back to the Moai. Because one of the most persistent assumptions about the statues has also been an assumption about resources. Hundreds of Moai were carved at the volcanic quarry of Rano Raraku. Many were transported kilometers from the quarry to ceremonial platforms around the island. Some of them weigh many tons. For decades, popular reconstructions showed those statues lying horizontally on wooden sledges or rolling across logs. In the collapse narrative, statue transport could therefore become part of the ecological mechanism itself. More monuments meant more wood. More wood meant fewer trees. The statues were not simply evidence of cultural achievement. They became evidence for environmental excess. There was always a problem with that reconstruction. Rapa Nui oral traditions said the statues had walked. That did not automatically make the tradition a literal description of engineering. Oral histories can compress metaphor, memory, ritual, and historical information into the same story. But archaeologists Carl Lipo and Terry Hunt began asking whether walking could be tested mechanically. The critical evidence came from the statues that never reached an ahu. Dozens of moai remain beside ancient transport roads between Rano Raraku and other parts of the island. For a long time, some researchers interpreted these road statues as deliberately placed monuments. Lipo and Hunt argued that many were statues abandoned during transport. If that interpretation is correct, their bodies preserve information about the transportation process itself. In a 2025 analysis, the researchers examined a database of 962 moai, including 62 associated with ancient roads. The road statues are not simply unfinished versions of the monuments standing on platforms. They tend to have broad, D-shaped bases. Their cross-sections and centers of mass differ from many moai after final installation. Most importantly, they lean forward. That forward angle seems inconvenient if the goal is to display the statue permanently. For vertical transport, it becomes useful. A forward-leaning moai can be rocked from side to side using ropes. As one side pivots forward and the statue changes its point of contact with the ground, the opposite side can then be pulled ahead. Repeat the motion and the statue advances in a controlled zigzag. It does not walk like a person. It walks like a massive stone cabinet being carefully rocked across a floor. Except the geometry of the object has been shaped to make that movement possible. The researchers tested the idea with a 4.35 metric ton replica based on the proportions of road moai. A team of 18 people moved at 100 meters in roughly 40 minutes. The experiment does not prove that every moai traveled this way. Archaeologists cannot replay the original transport events, and alternative methods have been proposed. But the walking model now explains several observations at once. The forward lean, the broad bases, the characteristics of the transport roads, the distribution of abandoned statues, and the Rapa Nui tradition that the moai moved upright. It also requires far less timber than the familiar image of gigantic log rollers. That removes another supposedly obvious link in the old collapse chain. The statues still required enormous skill, planning, rope, food, labor, and coordination. Nothing about walking them makes monument building trivial. What changes is the kind of society required to do it. You do not necessarily need a huge centralized workforce stripping an island of timber to move a multi-ton moai. A relatively small group, using a transport method adapted to the statue's shape, can move one vertically. And once that possibility is taken seriously, another question appears. If a smaller population could build and move the monuments, why were those monuments placed where they were? The answer leads away from the quarry and toward the one resource on Rapa Nui that no community could live without. Fresh water. Rapa Nui has no permanent rivers. There are no large streams cutting across the island, and rainfall can disappear quickly into its porous volcanic ground. For a community living there, finding reliable water was not a minor logistical problem. It shaped where people could live. That makes the locations of the ahu, the stone platforms associated with many of the island's moai, especially important. For decades, researchers had proposed several explanations for why those platforms were built where they were. Perhaps communities placed them near their best agricultural land. Perhaps the locations reflected access to fishing grounds. Perhaps the monuments marked territorial boundaries or visually important parts of the coast. In 2019, a team led by Robert DiNapoli tested some of those possibilities with spatial modeling. They compared the locations of 93 imaged Dahu with 3 categories of resources: agricultural land, marine resources, and sources of fresh water. The strongest relationship was with water. Along parts of the Rapa Nui coastline, groundwater moves through porous volcanic rock and emerges near the shore. At low tide, fresh or brackish groundwater can seep out between rocks or through the coastal substrate. To someone looking only at the surface, the island appears almost waterless. To people who understood its geology, the coast contained a distributed network of places where drinking water could be collected. The statistical analysis found that proximity to freshwater sources was a much better predictor of Ahu locations than proximity to the best farmland or to the marine resource areas included in the model. That does not mean every platform was simply disguised well. Ahu were ritual structures. They were associated with ancestors, communities, ceremony, status, and memory. Human landscapes rarely have only one function. What the mapping suggests is that ceremony and survival were not separate systems. Communities placed some of their most important architecture within landscapes, where access to a scarce resource also mattered. The Moai themselves usually faced inland toward the inhabited landscape rather than out across the Pacific. From that perspective, an Ahu was not an isolated monument built for people to admire from a distance. It belonged to a community. And if communities were organized around local resource zones, that changes how we should imagine the political system that produced hundreds of statues. A centralized state's not the only way to build monumental architecture. Evidence from the place where most Moai were carved points in another direction. Rano Raraku is the volcanic quarry on the eastern side of the island where the overwhelming majority of Moai originated. The quarry is famous for unfinished statues still attached to the bedrock and others standing or lying around its slopes. From the ground, the site can look like one enormous industrial project. From above, it is more complicated. A study published in 2025 used 11,686 drone photographs to build a detailed 3-dimensional model of the quarry landscape. Researchers identified at least 30 separate quarrying foci, distinct areas where carving activity took place. The pattern matters because the quarry does not look like a single production line under one centralized authority. Different parts of Rano Raraku appear to have been worked by separate groups. There are variations in carving zones, extraction strategies, and the ways different statues were connected to particular sections of rock. The evidence is compatible with a system in which multiple communities organize their own monument production while sharing access to the same quarry. That interpretation fits a broader picture emerging from the island. A relatively small population does not require a king commanding thousands of workers. Monument production can emerge from cooperation and competition among local groups. Each community can mobilize labor for a statue, organize transport, maintain an Ahu, cultivate land, and manage access to resources without the entire island functioning as one giant workforce. This does not make the system simple, it makes it decentralized. And decentralization may help explain something that has always seemed disproportionate about Rapa Nui. How could a small population produce so much monumental stonework? The question assumes that all the work had to happen at once. It did not. Moai production unfolded across generations. Quarrying, transport, platform construction, agriculture, fishing, and ritual life were distributed through time. A community did not need thousands of people permanently assigned to monument building. It needed enough people, enough coordination, and techniques efficient enough to make each stage possible. The walking transport experiments matter for exactly that reason. So do the rock gardens. So does the freshwater map. Each is a different response to the same underlying condition: life on an isolated island with hard limits. At this point, it would be tempting to reverse the old story completely. Perhaps there was no ecological crisis. Perhaps Rapa Nui was simply a model of sustainability. Perhaps generations of outsiders mistook successful adaptation for collapse. The climate record makes that conclusion too easy. In 2025, researchers published a high-resolution reconstruction of past rainfall using evidence from crater wetlands at Rano Raraku and Rano Kau. The record showed a major climatic shift beginning around the middle of the 16th century. Rainfall declined sharply. The researchers estimated that annual precipitation may have fallen by roughly 600 to 800 millimeters compared with wetter conditions before the drought. And this was not a single bad season. Dry conditions persisted for more than a century. On an island without permanent rivers, that is a serious problem. Freshwater availability would have changed. Agriculture would have become harder. Plant communities would have been stressed. Communities already living close to environmental limits would have needed to respond. Now the story becomes more difficult, because severe environmental stress really did occur before the worst 19th century demographic catastrophe. The older collapse model was not wrong to look at ecology. Its weakness was turning ecological stress into a specific demographic story without enough evidence for each step. Drought does not automatically equal collapse. A society can respond by changing crops, moving activity, intensifying some forms of cultivation, reducing others, sharing resources differently, or reorganizing political relationships. Archaeology can sometimes detect those responses. It can't always tell us how frightened people were, how much conflict occurred in a particular decade, or how individual communities understood the changes around them. This is where the evidence demands restraint. The absence of a severe genetic bottleneck before European contact does not mean life was peaceful. A relatively small population does not mean resources were abundant. The ability to move Moai efficiently does not mean building them was cheap. And a monument located near fresh water does not mean religion was merely a practical disguise for infrastructure. The stronger conclusion is narrower. Rapa Nui was experiencing real ecological constraints and later a prolonged drought, while the available demographic evidence does not show the catastrophic pre-European population crash, once treated as the centerpiece of its history. That is much stranger than either version of the legend. The islanders were not living in an untouched paradise. They were maintaining a society in a place where soil, water, timber, and rainfall could all become limiting. Their agricultural techniques suggest adaptation to poor soils. Their settlement and ceremonial landscape was closely associated with scarce freshwater. Their quarry appears to have supported multiple working groups rather than a single monumental bureaucracy. Their statues could be moved using methods that required surprisingly small teams. Then climate conditions became worse. And still, the clearest genetic signal of catastrophic population decline does not appear where the classic story tells us to expect it. So, if the famous collapse did not happen in the simple way it has so often been described, we have to ask a more precise question. When does the undeniable catastrophe in Rapa Nui history actually begin? For that, archaeology alone is not enough. The island enters the written record. The written record begins on Easter Sunday, 1722. A Dutch expedition commanded by Jacob Roggeveen reached Rapa Nui after crossing an enormous stretch of the southeastern Pacific. His crews encountered a living society, not an abandoned island. People approached the ships. Communities occupied the landscape. The monuments were still part of a cultural world Europeans barely understood. The encounter was also violent. During the visit, Dutch sailors fired on islanders, killing an unknown number of people. It was the beginning of a new period in which Rapa Nui would no longer be shaped only by the environmental limits and political changes developing within the island. Outside forces had arrived. That does not mean everything changed in a single day in 1722, nor does it mean Rapa Nui had been socially static before contact. The evidence from the 16th and 17th centuries points to real changes. Monument construction declined, ritual and political practices changed. The prolonged drought would have placed pressure on food and water. Deforestation had transformed the ecology. What the newer demographic evidence challenges is the claim that those changes amounted to a catastrophic population collapse before Europeans appeared. That distinction becomes clearer when we look at what happened afterward. European and other foreign vessels returned to Rapa Nui repeatedly during the 18th and 19th centuries. Some encounters involved violence. Outsiders introduced diseases to populations with no previous exposure to them. The island also became caught in the expanding systems of labor exploitation operating across the Pacific. Then came the raids of the 1860s. Peruvian slave raiders descended on Rapa Nui and kidnapped a large fraction of the population. A 2024 genomic study summarizes the historical evidence as roughly 1/3 of the islanders being taken. Very few returned. Those who did came back into a population already shattered by removal and violence. Epidemic disease followed. Smallpox was especially devastating. The population eventually fell to an estimated 110 people. Here finally is a demographic catastrophe that does not have to be reconstructed from a hypothetical curve. It is documented in the historical record, and its timing changes the meaning of the island. For generations, popular versions of the Rapa Nui story compress two very different histories into one. Environmental transformation and cultural change before European contact were treated as evidence of a self-inflicted collapse. Later destruction through raiding, disease killing, and colonial disruption became the final scene of a tragedy supposedly set in motion centuries earlier. Chronology is not a detail. If the population remained relatively small and resilient through the pre-contact period, then the moral story of unchecked growth followed by ecological suicide becomes much harder to defend. The newer evidence does not erase deforestation. It does not erase drought. It does not prove that Rapa Nui communities never fought, never experienced hunger, or never made decisions that damaged their environment. It says something more specific. The ecological changes we can document do not currently support the severe 17th century population bottleneck required by the classic collapse model. That conclusion now comes from more than one direction. The agricultural footprint appears substantially smaller than older remote sensing estimates suggested. Ancient genomes do not show the expected pre-contact demographic crash. The same genomes reveal pre-European contact with Native Americans, reminding us that extreme geographic isolation did not mean complete human isolation. The shapes of road moai are consistent with a transport system in which relatively small teams could move large statues upright. Ahu locations are strongly associated with access to scarce fresh water. Rano Raraku appears to contain numerous separate quarrying areas rather than one simple centralized production system. And the climate record shows that these adaptations were being tested by a prolonged drought beginning around the middle of the 16th century. None of those findings by itself explains Rapa Nui. Together, they change the question. Instead of asking why a reckless civilization destroyed itself, we can ask how a relatively small population continued functioning after it's first changed, while farming nutrient-poor soils, managing limited freshwater, building monuments, and enduring more than a century of worsening drought. That is not a story of effortless sustainability. Resilience is not the absence of hardship. It is what a society does while hardship is happening. There are still major things we do not know. Population estimates remain estimates. Remote sensing can miss archaeological features. Genetic effective population size is not the same as a census. We cannot watch the original Moai transport events. Statistical relationships between Ahu and water do not reduce those monuments to pieces of infrastructure. Climate records tell us about rainfall, not exactly how every community responded to it. Even the end of the Moai building era cannot be reduced to one cause. Drought may have contributed to social and ritual reorganization. Resource changes mattered. Political relationships changed. European arrival added new pressures and eventually much more destructive external forces. Archaeology is replacing one simple answer with a more complicated history. That is exactly what good evidence is supposed to do. The old version of Rapa Nui was attractive because it functioned like a fable, a tiny planet in the Pacific, a society consuming its last tree. Monument builders too obsessed with status to recognize that their world was collapsing around them. It was easy to remember because every part had a moral purpose. The real island refuses to fit that cleanly. Its forests disappeared, but the people persisted. Its rainfall declined, but the population did not leave the severe pre-contact genetic collapse once expected. Its giant statues demanded labor, yet experiments show that moving them may not have required armies of workers or forests of rollers. Its ceremonial platforms honored ancestors, while their locations were also closely tied to the geography of water. And when catastrophic depopulation finally becomes unmistakable, the story is no longer simply about what the Rapa Nui did to their island. It is also about what outsiders did to the Rapa Nui. That does not turn the people of Rapa Nui into perfect environmental managers. It should not. Replacing one myth with another would teach us nothing. What the evidence supports is more interesting. Generations of people adapting to an unusually constrained environment, sometimes changing that environment dramatically, surviving climatic pressure, reorganizing their society, and continuing forces arriving from far beyond the island transform the scale of the crisis. The Moai remain the most visible part of Rapa Nui, but they may never have been the best evidence for collapse. The better evidence is quieter, a fraction of a square kilometer of cultivated stone, a demographic signal hidden in ancient genomes, a fresh water emerging through volcanic rock, the angle of a statue abandoned beside a road, a drought recorded molecule by molecule in the sediment of crater wetlands. Each one corrects a different assumption. And together they leave us with a warning very different from the one Rapa Nui became famous for. The danger is not only that societies can damage the environment supporting them. That is real, and Rapa Nui certainly experienced profound ecological change. The danger is also that once a story becomes morally satisfying, we can start treating every piece of evidence as confirmation. Rapa Nui does not need to be a parable. Its history is already enough. And the more carefully we measure it, the less it looks like the simple collapse we expected to find.